तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We will continue with the Verilog DCTQ controller design, and we stopped last time here for ready signal, and ready signal is turned on only if this condition is met. This condition is given here so long as the start is asserted and we have the counter 0 1 here. This implies that we have already processed DCTQ for the previous block, and we are about to start, in fact started already the current block, and just at the beginning. And so while at this stage we can allow this host to write data into the other RAM which has whose value has been already processed, and that is what we are doing here. And at this end only when this condition is satisfied, and if this is not satisfied, so ready will get this inversion of start reg, and for example if it is 1, so it will not make it ready, and that means there is no start signal. And on the other hand, if start is asserted and count value is something else, and then also this won't be satisfied, and therefore this will be 1 will be inverted, and it will continue to be low for other counts as well. And here we produce DCTQ valid signal, and in order to have this we have to have one more signal which we will see why it is, and during reset we reset both these signals, and if a hold is encountered, so what we do is then DCTQ valid must be switched off, because the DCTQ processing is held now. So valid signal also must be withdrawn, that is why we are doing here. And so you remember that the pipeline was 45 for before DCTQ starts out, and DCTQ valid goes high only at this stage, because of this it is going, and that is for the counter 1 being equal to 44. And now, and at this stage we also make this signal 1, and for this purpose, for example after this it keeps on processing, at that point of time let us say the hold comes again. So what will happen, DCTQ is forced to 0, and once it is withdrawn it will come to this stage. So, what will happen here, and earlier it was DCTQ 1, but because the hold has come it was forced to 0, and how to retrieve this when hold is removed and continue from where we left, that is possible only if you make this once again 1 from 0. That is possible by copying this contents into DCTQ value, which we do here at this step, and if nothing else, then we just preserve the contents. And next is signal is start reg, which we have been using before, and for this the condition is start equal to 1, and this is, mind you, it is not a start register or start next, but actual start input itself, and when the start input is applied, and it will be sensed only when counter 1 is 0, and then only it will assign 1 here for the start reg, that is this condition here. So, this will take place 1 clock cycle later, and in the next case, suppose start is 0 and then counter is 62, implying that it is the end of the DCTQ processing, nearing the end. So, what happen at that point of time, if start must goes to 0, then it what should happen, it must reset the start here, and that is what it does here. This completes the controller module, and so what we have to do is do the test bench. DCTQ test file is this here, and we take a lina.txt as the input file name, and final output will be DCTQ.txt from same. So, as usual for the test bench we run at 100 megahertz, therefore, this variable is put at 5, and another clock also put at the same thing. We define a variable called number of blocks to indicate how many blocks there are in a 256 by 256 pixels, each block being 64 pixels. From this we can get this, and this is the design module which we include here, and then start the DCTQ test module here, and reg are all inputs that we need to declare here, and wire as the outputs. Notice that DCTQ, its validity and address are all wire, and we also need a counter for end of block, and also a signal called stop processing, when to stop after 1024 blocks are processed, and so on. So, all these are used here, and when a particular block is ended also should be known, and when the test bench must start the whole DCTQ processing is governed by this signal. So, if you want a different picture, we had to change the blocks, and all the statements to be changed is listed here, and we have in test bench we have a counter here that keeps track of the number of blocks processed, and DCTQ output file is contained in FP1, and what we do is first we read a disk file and copy it into a memory array. This we have seen before in external memory design earlier, and here we have 8192 total here, each being 64 bits, and this much memory is required in order to have 1024 blocks of the 256 by 256, and this related in terms of number of bits. For address you need 13 bits in order to address this, because it is nothing but 8K, and that is what it says here, and we now invoke the DCTQ design and list all the IOs therein here, and then we start the initial block of the test bench. So, in the first step what we do is we read the lina.txt, which is the actual image file in a text form, and put it in the memory which we have declared earlier as regmem, and that is what this command does. $readme in hex format is the instruction for that, and then we need to identify the output file, which we do here, and also say ask it to open that. So, this is the command for that, and is the DCTQ output text is the output, and derived from the lina.txt, which is the input, and herein what we do is all the inputs we initialize here, and this one these are all the signals that you are already familiar. So, we will not go into the details, and So, I is a counter for which we have already said before, and now at this point of time we apply the reset. So, active low here for 20 nanosecond and withdraw, and then give the start signal. After once you give the start signal, because we have invoked the DCT design already, and it will start functioning, and after say 700,000 nanoseconds it will the file will be closed and stopped, and during which time you would have already processed one frame of image and got it in the dctq.txt as output file, and this is a statement for inverting the clock so that the clock can run for both the clocks. We now have an always block to take further decision, I mean process block after block. How we do, we will see. We need to take action only if start is 1, which we have already made 1 there, and at positive edge of the PCI clock what we need to do is we have to read the image block and input it into the actual design, and so before we do that we make sure that all the blocks are not already processed. That is why I checks for not equal to 0. So, because I was initialized to 1024, so block after block this will be decremented and checked here, and at positive edge of the clock what we do is we make that data invalid, because we are going to input the very first block there, and which can be got from the memory which we have already stored, that using that read memh, we have already stored the disk file into the actual memory, and from that we start reading from right from first location, that is a 0 location here, and input to the dual RAM here. This is nothing but DCTQ design core, and every time we do this we increment the address so that we go to the next location and keep on writing row wise in a block. So, you need 7 more times in order to complete one block, because there are 8 such rows, and that is what we do here by repeat here, and this is the block which does precisely the same here, are all exactly the same. So, next what we do is we wait for ready to go high again, because DCTQ core has started functioning and it is churning out the first DCTQ block. Once it is complete, it will assert ready, then till that time we do not input here, and so only at this point of time what we have done so far is we have merely input one block of image data into the dual RAM. So, now we have to start the DCTQ process, so that can be done only by asserting the start signal here, and we keep repeating this for block after block. That is why we are decrementing from 1024, then it becomes 1023 and so on, finally it will become 1. When it becomes 0, it quits the always block we have seen before, and in addition to this, so we have to have a counter for counting number of blocks processed, and then compare it with the number of blocks we have already given at right at the beginning, which is 1024. So, when the 2 equals, this is the running counter, and then we stop, so and close the file, that is what is here. So, next thing is we need a signal called stop process in order to stop the entire thing after one frame is already completed, DCTQ value computed and stored in dctq.txt file, and this expression does that precisely. The running counter is examined for number of blocks, and also we see that end of block is also 1, only then we take this action, and if that is not met, that means DCTQ processing is still going on. Only then we write into the output file, which is dctq.txt, and if it is 1, we will not write here. So, that means stop process will go right at the end of all the blocks being processed. So, in the next step what we do is we had used end of block. This is generated by just examining address equal to 63. This is the running address of the DCT coefficients, and 63 means it has just now processed all the 64 coefficients. So, we set it to 1, otherwise we set it to 0, and that is how we count this in the next using advanced increment for the end of block counter, and which we process here, and whenever this end of block is 1, only then we increment the thing, that is how it is taken care. This completes the test module as well. So, here we have the simplified results for the DCTQ processor, and you will notice that it operates at about 100 megahertz here, and this is the device, very same device we have used for RAM, ROM and multipliers, adders, etc. earlier, and it lists all the primitives that it has consumed. This here too, and then it has taken 16 by 1 RAMs, 128 in number, and it has taken 3728 which is 25% roughly of 600,000 gate capacity FPGA, and in Xilinx we will have a little more optimization here, maybe 3200 here, and this may remain same. The input for Xilinx is DCTQ.edf, and which we generated from Simplify, and it has mapped the same device, and it lists number of slices, etc. You notice that number of LUTs it has optimized from 3700 to 3200, and number of gates count for this particular DCTQ design is around 124,000 gates here, and we will see the waveform, so that we can verify whether it has functioned correctly or not. So, these are all the different signals listed here. The signals are over 100. It is physically impossible for us to take all the signals. The vital signals we will examine here. So, for example, this DCTQ is here and its validity is here, and notice that no DCTQ is coming over here. These are all different counters we have used, and one R and W signal also we will examine. And in this first thing, what is happening is DI gets the dual RAM input, gets the first block of data. This is DIN valid, and you can see here this a counter running here 0, 1, 2, 3, and precisely at that point data is input and data invalid also is high till 0 through 7. That means 8 such writes are possible. Each write will be total 8 bytes here. You can see 16 digits of hexadecimal. So, and once then it data in is withdrawn, and after a while only it will be written here, and this signal is the ready signal that you have at the bottom. So, it is normally ready, and then when the first data is written, it temporarily it will be withdrawn and once again asserted when counter is 1, which we have already seen in the design. And here just remember one aspect here. I think we are starting here, the start pulse is here, the start pulse is here, that is the third waveform, and it is happening right at this point of time. And although this is happening at this point of time, it will be recognized only at the positive edge. It has missed the clock marginally. So, this edge will be noticed only here, and once it is noticed, the start is converted into another start edge which we have seen in the design, and that will come only one more clock cycle here, and therefore, only at this point of time where this is 0 here is the actual start happening there. So, corresponding to this 0, you can see this is also 0 here. This is nothing other than counter 1. So, this is that different counters we had used for keeping track of the pipeline, and so you would notice, let us just remember when this 0 starts, and that corresponds to say 185 nanosecond here, right at this point, right, and simultaneously at the same point R and W also switches control from 1 to 0, so that another RAM can be written here. So, now what we are going to do is counter 1 is 0 and starting to count implies that the first block of DCTQ is going to be processed right from here, and so this because the start pulse takes effect only here. So, this happens to be 185 nanosecond, which I have noted down, and let us go on to the second one and see what it has to tell. So, you can see that data in being applied once again, it is not applied right here because it is not at time. So, what is happening here is actually this counter 1 is still running, and you can see it has just crossed only 10, 11, etc. So, at this point of time what is happening is and precisely when counter is 15, we have seen in the DCT controller, then only counter 2 must stop. This all the likewise counter 3 will stop only for 20 actually. So, here and although it appears to be 21 here, and it is actually 20 we have enabled the counter. The actual counter itself will take place only 1 clock later on, that is why it is deferred here. In fact, you can see right here the 0 must coincide with 20, that is what the implication. So, we have precisely got the same thing earlier for 15, you can see 15 and 15 start here, and here I think I have to examine that. So, I do not clearly remember what value it is, and similarly this for the next counter 0 is 20 we have seen. These are all the pipeline. If if you make a single mistake, even 1 clock cycle this way or that way, you will not get proper output, everything will be totally in disarray, and this is what the waveform says, and this one gives further say we will straight away go to DCTQ and the counter here, further counting has taken place for the here, and now at this stage the last counter has gone, it is counter 4 here, and it is happening at 35, you remember 35, you must be remembering 20, 35 was okay, and then it starts counting. Similarly for DCTQ, address also will be given by the last counter, that will take place only at some 44 or so, you can see 44 right at this point of time, and now you notice that this is the DCTQ, the very first DCTQ block has come only after the 45 clock cycles, so right from the start. So, at the start it was 185 nanosecond, now let us see how much time this is occupying here. This one is 635 nanosecond. So, if you take the difference, you get precisely 450 nanosecond, which means 45 clock cycles, because our time period of 100 megahertz is 10 nanosecond, and precisely after the latency of 45 clock cycles you have got the first output, and this is the DC coefficient, balance are all AC coefficients, and there will be totally 64 in number. If you go through that, we will go into the other waveforms. So, we will go straight away there. So, now you can see it has completed the very first block data writing. So, counter 1 is for the DA input for the dual RAM here, and it has completed here. So, because it has completed, R and W is once again automatically switching. So, not a single clock cycle is wasted. So, it is a continuous firing of input image, so also the output, and output also you can see here, and this is not yet complete, we will see in the next waveform. In the next waveform, you can see this is the address for the coefficient, and you can see here the coefficient number is 63, which means 64th coefficient is just now processed, and immediately without any wasting clock cycle it starts processing the second block, next block. So, at this point of time it is 12 and 75 nanosecond. The start of the block was at 635 nanoseconds we have seen. If you take these two difference, you will get precisely 640 nanosecond. If you divide by 10, you get 64 clock cycles. So, exactly our claim was every coefficient is created at every clock cycle. So, this is proved and it is continuing here, and that is what we want to see there, and it keeps going there, and we have some more waveforms. This is towards the end of the all the 1024 blocks being processed. So, that is the start here. This 4B now shown not in decimal but in hexadecimal, just for a change, because the output file derives only in hexadecimal, and you can see that AC coefficient here is first AC coefficient is 8, other things are 0. So, as we mentioned before, DCTQ succeeds in making most of them zeros, only few non-zero coefficients will be there. First coefficient will always be a very high value, that is for DC coefficient, sorry, and this is the last of the previous last but one block that is processed here, and so towards the end it keeps going. So, in the next, this is the last waveform. Let us see towards the end of the block, very end, we have what is called a stop processor processing after all the 1024 are done, and now you can see the last quotient is 63, this address, and you can see completely not a single cycle wasted anywhere, and you can in a minute you can verify that. See, at this point of time stop process goes high, so that means indicating all the 1024 blocks are processed. We started the processing at 635 nanosecond, now we are ending the process at 655995. So if you subtract the 2, you will be getting 655360 nanoseconds. So that knock off that 0, you will get it in clock cycle, that is 65536 clock cycles it has taken for 1024 blocks. Each block is 64 bytes, therefore it is 65536, which you know as 64K. So you see the entire image has been processed exactly 1 pixel 1 clock cycle. This proves the first statement we made at the time of explaining the algorithm. We have completed the design of DCT-Q. In a similar fashion you may have to do on your own IQ IDCT, which is just inverse of DCT-Q, and we need to verify whether this DCT-Q IQ IDCT course are functioning properly. In order to do this, we will have to resort to MATLAB coding, and which we are going to cover. And before we start the MATLAB coding, let us see what we need to do for verification. I will just read out here: invoke MATLAB and run the following file for reading an image disk file which is in raster scan order. So the disk file is lena.ra, and you need to run this file in MATLAB after invoking the MATLAB. So you have also to specify what is the size, and you want to process block by block. 8 indicates 8 by 8 block, lena is the file name, and execution of this file it takes about 10 minutes, and depending upon the computer that you use. And another disk output file lena.text, which is in block format. Now it is converted into block format because we want to simulate now. So we had to change the raster scan to block format only, that is what we are doing here, so that we can use it in model sim. And next step is to invoke the model sim and compile DCT-Q test bench, and also load. You can use these commands instead of menu, which we have seen before earlier, and also invoke the waveform and signal, select all from menu, run all command. Then DCT-Q output is created as a disk file DCT-Q.text, it takes about 5 minutes. So DCT-Q has produced the result, and that will be in DCT-Q.text. This will be precisely what you have seen as the waveform, say 158 etc. You have seen all that will be contained in this here, and that will be in basically in decimal format, in hexadecimal, or rather binary, because we are dealing with the hardware. And next step is to invoke the IQ IDCT, and it is inverse, which is left as an exercise for you, and hoping that you complete, then you can run this. So once again you do the compilation as well as load the design, and then invoke the signals, and then run the same. So when you do that, it will take DCT-Q.text got in the previous step, and do the inverse operation, and thus reconstruct the picture, and it will have IQ IDCT.text as the output, and once again it takes so much time. This will be in the block order because we have converted into block earlier. So in order to see the image in the right perspective, so we need to once again convert this block order into raster scan order, which we do by invoking another MATLAB program, and it takes this one where it was created in step 3, and this is the command you had to run, this is the file you had to run in the MATLAB, and IQ IDCT is the file, and execution of this creates another file called IQ IDCT.raw, and which is in raster scan order, and this will automatically be done in raster scan order. When we see the MATLAB code, we will understand that. File for displaying this reconstructed image as well as the original and lena.image. What we need to do is, next step is, we have got the reconstructed output as a file, and also we succeeded in converting into a raw file, which is raster scan order, and we need to show this, and so that we can visually see the picture and compare. For example, original picture lena.raw and this reconstructed thing can be compared visually, and then you can make it out whether the picture quality is good or not. So, and in order to have some ready reckoner, you also have a computation what is called a PSNR, it is a power signal noise ratio, and it is conducted over the entire image from reference image, that is the original image, and the reconstructed image. So, for this also you need to run another MATLAB code called show image for showing and psnr.m for computing the PSNR codes. So, we have said before we need to download this XN view software that is available in this, you can download from this site. You can use that XN view in order to convert from one format to another, raw to TIFF format, etc., which we will be needing for the MATLAB code running. So, here comes the MATLAB codes. So, this is the top module. In order to read the image here, and we declare that as a function, we give the file name, number of rows, block size, etc. An example is given here, and we also have to declare the input file in as a raw format and output file as text format, because we need to get lina.text here, which will be inputting this to the model sim. So, that is what we are trying to do here. We have to declare it as a read and write here after opening the files. It is here we actually read the file, read the input file which is in REST-scan order, and next we this is a variable. In order to after reading, it will be a this image will be put into a 1D vector. Then call the image read function to organize it into blocks. Then that is what see this for details. We initialize a variable here, and this is a pixel counter, and they are all C like structure. You have a for loop here, start end point here for k, I, j. The innermost loop is this one, and what we are trying to do is we have a REST-scan order image that we are trying to convert it into block. That is what we are doing here, for which we need 2 dimension I and j. So, there are 8 by 8 pixels, therefore, it is 1 to 8, 1 to 8. Like this we have 1024 blocks in an image, that is why this variable is for. And then we also increment every time the number of pixels counter. And then we know another module which we will be explaining a little later, and convert output this one block we have got into a disk file for use in the next stage, and then close all the files. So, the image read is the function we had called earlier, and that is what is here declared here, and once again that is available as x here, and we initialize here, convert all elements to 0 here, and once again we have for loops here. The first loop is we have already got one block of pixel. So, like this there may be several blocks along the horizontal dimension of the image. So, we will call that as a row block. It is a row for the block, that means there are 8 rows there. So, 8 into 256 pixels will be covered in one row block, that you should understand. And how many such rows vertically in the picture is governed by this I here, and that one you can have from it starts from 0, and it advances as I mentioned in the steps of 8 into 256, and then the last one is for the entire 256 into 256 all the pixels minus this particular step, because that is the last row that we need to process, and and then within that row block we need to identify block, which block we are processing, and that is done by this j variable, and I is another, it starts from 1, then each block is 8 pixels in width, so each block, so it advances by 1, then 9, then 17 and so on. The very last block will be 249, and the end of that pixel will be 256, so 8 pixels there also. And here, and we have one more loop for k and m. This is to process a particular block. So, this will be done by 0 through 7 here, and if you take one example it will be clear to you. For example, and what we have processed, we are writing it into matrix X, which is a 1 dimensional vector, right, and if you take one example, the very last in the row block, if you take that one, you remember that 249 was the last there, and that is for j, and this is 7 here is the last one, and m is also 7 for the last block. So, the column is 256, so this is here. So, it precisely turns out to be 8 into 256. This implies this is the last pixel that we have processed and put here. Is that clear? And this is in 1D vector, and that is what is meant here. So, next one is to write this block. What we have done before is we have got into arranged it into a block and then we had to write it into the output file. That is what we do by this file. And in this case do not just ignore this one, and we need to arrange the block in ij form. This is the form in which we have already input. So, we need one more counter here, j equal to 18 and I counter also, and here. So, we have to process one block. So, that is why it is given as 1 to 8 and block is precisely the same thing. So, it is arranged as 8 by 8 matrix here, and that is copied into a number here, and that number will have to be converted from decimal to hex, because what we get from the raw file is actually in decimal format. So, all the image, and so we had to do that here, and what we do is we just append every time we process one pixel, we append into another hex string 1D vector here, and finally write that particular thing, the same variable, into the output file. This is that output file corresponding to that lina.text or whatever name we have given, and it should be every time you write a new line must be taken into account. So, every alternate next line you have to write. So, what you have here is all arranged in a single file, pixel after pixel, arranged in that fashion. Write into the output file each pixel in a new line. That completes the writing into the file block by block. And now what we had to do is, after we have seen verification, in that step, this is the step for the DCTQ running. After that you will run the DCTQ, then its inverse IQIDST. Finally, that also will give you a reconstructed picture. So, that will be in block format, and that will have to be converted now into rasterscan format. So, for that you need these MATLAB codes. This is called a write image file, and it takes the reconstructed image and converts the block format into raw format for displaying using show image. You need this also we have seen before. We will first have a look at this. These are all usual file name, whether it is text format or raw format, whether it is read or write, and this is the one we read from that file. FP1 is the first one here, file in. So, if it is lina.text, that will be read here and put in this variable here in decimal format. See, note that it was in hexadecimal, the IQIDST was still in binary, actually hexadecimal we can say. That must be, it was converted earlier, you remember, in read image. Now we had to do the decimal into decimal conversion. It is a simple thing like a C like instruction there. So, here we call this image write once again, as we did in image read earlier, and then finally output that result into the final output. You can treat it as a character string, and this will be in the row wise into in a rasterscan order finally. So, this is the function which converts that block into rasterscan order. This is a function we are going to call, and that was a higher level program just now what we have seen, which calls this one. So, here you will have this rasterscan, this exact counterpart of read image read, which we have seen before. So, we can quickly go through this is a declaration, and this you remember 0, 8 into 256, the entire row block I was saying. So, we have now to write a block which is confined to, say, it starts here, then goes to second line and so on. It will be a block like that. Now, what we have to do is write first line of the block row first, and then go to second row of the block and write alongside the first here, so, and repeat the same thing in the same fashion till you have exhausted all 256 thing. That is what we mean by rasterscan. That is what we are doing here. That is the pointer there for that. And as usual, we have some more variable j and 0 for block processing. This is with block within the row block processing and so on. So, only difference is this was there on the right hand side at that time. Now, what we have is block by block block arrange image details. This is pixel value for there are so many pixels then that many data will be there in 1D vector, but arranged in a block fashion, and that is got here, and now it is arranging as we have seen before into a raster scan order. So, it goes right up to the last very last 8 into 256 pixels, that shows that it has converted correctly, and for every pixel we advance, this is a pixel counter here, and corresponding end for loops. So, this is the module for showing the image, and that is the image. We have two files, one is the raw format Lina, this is the original thing, and we now have IQIDCT created by that right image here as a raw file, and here we have two loops for covering all the pixels in horizontal. This corresponds to the horizontal width of the image, and this corresponds to the height of the image. So, all the image pixels are covered here, and what we do here is we arrange it in 2 dimension here, and we convert first the image one is the actual read from that file, and that one we have to convert it into double format first, and then make it into 8 integer. This is the requirement for using the MATLAB command which we will be covering later on. That is the requirement from the MATLAB. So, you had to manipulate conversion. So, and every process pixel you process, you just increment that, and finally you open an output file here, and image 2 is that output file, and this is for the second one reconstructed. What we are trying to see is show image. So, we have processed so far the actual original file, now we are going to process the reconstructed file, that also is exactly the same here. Once again we take the double and then uint, and then put it as a reconstruct matrix ij. Ij varies from 1 to 256, and n plus 1 is to increment the pixel counter. So, once we had done with this, we have processed and got it in original and reconstructed matrices, the actual original image and reconstructed image. What we had to do is just display. For that, there is one command called imshow, and this is the format you have to do. This demands that uint double precision we have used earlier, and because of this requirement we had done that, and it shows straight away right on the screen when you execute, and you can also give a title if you wish here, and once again show the that was our original file. Figure 2 is for the reconstructed file here, and you can compute the PSNR value, which is very simple here. So, what you need here is you need to use section view and convert that raw file which we had got just now and into TIFF file, then only you can execute this, and this 2 files are here, and for which we need to compute. This is the reconstructed file, this is the original file, and we need to compute the PSNR. So, we have what is called 2 variables, original and reconstructed, and we use a double precision here, and mn is the size of the actual image, and PSNR computation is governed by this expression, which means 10 log 10. Then you have on the numerator you have 255 square multiplied by m into n, which is nothing but picture size, in this case 256 by 256 for Lina, and divided by the numerator here, which is nothing other than pixel wise intensity between the original and reconstructed figure, and every pixel difference you get rid of the sign by squaring it, and then finally summing for all the pixels, and that is the denominator. If you do this, you get in dB decibels the PSNR value, and here dot means element element to element. So, this is not the entire file, that is the meaning. If for example, if you take a Lina image, I have also done DCT as well as IDCT course, which needs change from DCTQ IQIDCT, and in which case you get a very high PSNR value, this 38.9 dB here, and if you apply DCTQ IQDCT in Verilog for this Lina image, I get a PSNR of 29.4, which is very close to MATLAB DCTQ IQDCT, which serves as the reference for checking this, and this particular thing is not explained in the present course, and it is left as an exercise for you to evaluate DCTQ, and which is merely manipulation of matrices. So, it is very easy for you to do that, and compression affected also will have to be incorporated in that, unless you do the VLC course you can't have that is also covered in that one, and from which you get this compression ratio to be 12.28 for this particular image. Now let us have a look at the results or the image. So this is the original image. Here what you see here is the actual original image, and from MATLAB after DCTQ, IQ, IDCT you get this image. It may appear to be close, I do not know how it appears on the TV monitor. Is there a difference between the two? I am not sure, and probably you can see some quality suffering here, and this is DCTQ, IQ, which we reported as 29.4 decibels here, and this is Verilog created DCT, IDCT, and you see a very high decibel here for this. It is as good as the original. So a good quality picture is supposed to be 30 dB and above, and a bad quality is 25 dB and below, and indistinguishable quality you will get if it is 35 dB. That is the thumb rule for finding out how the picture is, apart from the visual findings. And this is for the reconstructed by Verilog. This is actually DCTQ, IQ, IDCT applied here. So you can see that this is very close to the reference from the MATLAB thing. You can see some say this is better than that, but opinions are divided. So the point is you have fairly good image, and you are able to process at a very high rate, and that is what you have here. Now let us have a look at the implementations I have already done for DCTQ. ASIC also has been done, so also the FPGA, which you have seen to be 124,000 for DCTQ gates count. If you extrapolate area which is reported in ASIC design in 0.13 micron technology, you have only 68,000 gates for the same design, and very same design works on the ASIC platform on Synopsys design compiler, and it works at 270 megahertz, whereas Xilinx we have seen to be 102 megahertz after Xilinx place and route, and same thing was done for the other cores, for example IQ, IDCT, DCT and IDCT. The results are here, and IQ, IDCT 80,000, whereas FPGA is 114, and again speed is hit here. So this governs the speed of the overall system, because at the decoder end we need IQ, IDCT. If it is motion picture processing, we need even at the encoder stage, and DCTQ is processed at 102 megahertz, but this is the slower of the two, 81. So let us see for that, and similarly for DCT and IDCT. These are all the capabilities of the IP cores that we have developed. And for processing a motion picture at 30 frames per second, each of the processors DCTQ, VLC, VLD, IQ, IDCT need to execute one picture frame in 33.33 millisecond or less. Therefore, the picture size is governed by this expression, which you can very easily derive, and where f is the frequency of operation in megahertz, and m and n are the width and height of the picture respectively. And if it is true color processing, is valid for both monochrome and color, 24 bits true, and pictures assuming all the three color components Y, CB and CR are processed concurrently. If you process concurrently, you need 3 times the chip area, but you will get a very high speed here, and the latter case demands 3 times the chip area than the former. Presently full color processing is not covered by the MPEG standards. So this in MPEG standard what is covered is we have seen before 4 blocks for Y luminance and 2 blocks for CB and CR. So this is only 6 blocks instead of processing for full color we need 4 into 3 times. So this is just half that requirement. So you can process much higher thing. So as a result the free, picture that you can process in this scheme will be governed by instead of 3 there, now it is 4.5 here. So 3 to 4.5, that is the difference between monochrome and this, because here it is 6 blocks, there it is 4 blocks, and maximum picture that you can process is tabulated here. If you take FPGA implementation here, this I have taken 81 megahertz as 80 megahertz here for this case. ASIC is 270 megahertz, and maximum picture size that you can process is 1600 by 1600, so very high resolution, and unfortunately we do not have other hardware matching this speed, although this is in spite of low frequency for IQ IDCT, and in fact I got 100 megahertz some couple of years back. I am not able to reason out why I got 80, it actually went to 1 or 2. So anyway I will take the worst case here, and if you take ASIC it will be a very huge resolution that you can process of the order mentioned here, and if it is monochrome or full color this is the case. If it is as per the standard in this ratio 4, then 1 block, 6 blocks instead of 4 blocks for monochrome, and actually the standard sizes come in this format, say 1600 by 1200 and 1024 by 768, which is called XGA format, and this is called SVGA format 800 by 600, then QCIF is 352 by 288, and this completes the DCTQ design. Thank you.